Hi, this is a short video lecture on Huffman codes for those of you who like this type of teaching. And if you like the idea of filling in a paper copy as you go, this blank worksheet is posted as a PDF on Learning Studio, so you could pause the video, print that out if you want. Here's our task. We have a long passage of letters, A through F, and so maybe the passage goes D, A, B, C, F, A, C, A, D, A, B, and so on. And as is often the case, the frequency of the letters are not equal. Some letters are far more common to be transmitted than others. If this were regular English text, E would be the most commonly occurring letter. Here, for whatever reason, A is by far the most common letter. We want to send this over a binary channel, which means we want to convert this string of letters to a bit string of zeros and ones. And because the passage is long, efficiency is an issue. And so we would like to come up with some way of coding these letters that minimizes the number of total bits that needed to be transmitted over the channel. So the most obvious thing to do is a fixed length code. If I used 1 bit, then that could be either 0 or 1, so I could represent 2 different letters. That's not enough. If I use 2 bits, then I can represent 2 squared or 4 different letters. That's not enough. If I use 3 bits, I can represent up to 8 different letters. That is enough. So we use 3 bits, and then if I just count in binary, there's no real reason to do otherwise. And there would be a code word for each of the letters. And then obviously you convert DAA to corresponding strings of zeros and ones and go for it. We can represent that in a tree. Here is the tree for code number 1. So first of all, notice that the information, the letters themselves, are all down here in the leaves. And each letter is matched with its frequency. But along the way is a tree structure, and in the nodes of the tree are the frequencies of everything in the tree yet below it. So 100% or 100 letters are below the root, and then 86 letters are below this, 28 letters below this, and so on. And then on the links or edges of the tree are the bits themselves. So D is coded as 0, 1, 1. And then when you get a word to decode, if you get a 0, 1, 1, it's a matter of going to the root. I got a 0 first, then I got a 1, then I got a 1. Oh, that's a D, and then I'm ready to go back to the root and wait for the next letter. So the number of bits needed to code a particular letter is actually the depth of the leaf in this tree. And so if I want to talk about the total number of bits needed to send the string using number 1, code number 1, n will be the number of letters. F sub I is the frequency of the ith letter, and D sub I is the depth of code word I in the tree, which is just the same as the number of bits. And so for code word 1, the total number of bits, well, I have A's to send. So A is at depth 3, or 3 bits needed for each A, and then from my table above, there were 45 A's to send. And then B's are also at depth 3. Everything is at depth 3 in this tree, and 13 of those, C's, 12 of those, D's, 16 of those, E's, 9, and F's, 5. And if you work this out, this is 300. I would need 300 bits total to send this many of each letter using this code. Can we do better than that? Well, notice that we're not making use of the frequencies very well in terms of efficiency. A is being sent by far the most often, and yet it's using 3 bits each time. F is not sent very often, and still we're using 3 bits for that. Maybe it'd be better to have a variable length code word where the most commonly occurring codes had the shortest word lengths. That's exactly the idea of Morse code, by the way, the telegraph code, where letters like E and T were a dot and a dash, and then less common letters would have longer strings of dots and dashes. So for example, I could do 0 and then 0, 0 and 0, 1. I'm just sort of making this up, but choosing, again, short words for commonly occurring letters. Could do that, for example. Big problem. So suppose coming in, I receive the bit string 011 0 001 011, and I'm receiving this and starting to decode, and I get a 0, and okay, is that an A, or should I wait for the next bit, at which case I get 0 0? Okay, is this 2 A's back to back, or is this a B, or should I be waiting for something else? So when the end of a code word is not clearly signaled, then it becomes challenging, maybe impossible, to uniquely decode the message. By the way Morse code handled that was that there was a pause between letters. The telegraph operators would put a slight pause between letters. But if you're handling this on a binary channel that's being transmitted over the internet, we have variable time delays and so on. And so having a physical time pause between bit characters is not very feasible. So let's discard this as not being very workable. What we want instead is a prefix code in which the beginning of one code word is never another entire code word. So let me show you an example. If I put a 0 here, because that's the most commonly occurring, and then I'll do a 101 and a 100 and a 111, 1101 and 1100, and it's feeling a little uncomfortable, like, do I really need that many bit strings, that long of words to represent these letters? Notice the long words are on low frequency letters. And furthermore, notice that no code word is the beginning of another. So now when I receive a bit string like this, I receive a 0. There's no question that was an A. Then I receive another bits that was an A. Then I receive a 1, 0. Well, that 1 is not a word. 10 is not a word. 101 is a B. And so there's no problem in decoding. This one would be a non-prefix code. Here's the tree for code number 3. And so notice it's deeper. This tree has depth 4, but again, the least frequent letters are the ones that are deep, so maybe that's not so much of a problem. Notice that this tree is not balanced, and notice that these are not binary search trees in any sense. I'm not claiming that when I go to the left I get the low letters, and when I go to the right I get the high letters. It may work out to be that way, but the frequencies are what's controlling the position in the tree, not the alphabetical order of the letters themselves or anything like that. So let's calculate for number 3 total bits required. So for the A's, they are at depth 1, and I have 45 of those. The B's are at depth 1, 2, 3, and 13 of those. For C's, 3 times 12. For D's, 3 times 16. For E's, 4 times 9. And for F's, 4 times 5. And that works out to be 224, which of course is considerably shorter than 400. And the reason is we save so much here on transmitting A's. So it's a variable length code, and it's a prefix code. It's easy to use. When we get a bit string in, I got a 0. Okay, that's an A. Back up to the root. I got another 0. That's to the A. Back up to the root. I got a 1. Okay, then I got a 0. Okay, then I got a 1. Okay, that's a new character. That's a B. Back up to the root, and so on. It turns out that number 3 is actually optimal in some sense. So let's talk about constructing an optimal tree. And remember, this whole unit, or this whole chapter, is on greedy algorithms. And so this Huffman coding for constructing an optimal representation tree is an optimal method achieved through a greedy algorithm. Very easy. I arrange my letters in increasing order of frequency, and I pick the 2 lowest frequencies. I merge them. So 5 and 9 are going to go into a subtree. I always put a 0 on the left branch, a 1 on the right branch. That's completely arbitrary, but it's just as good as the other. And now 9 and 5 together are 14, and so let's put that weight in, or frequency, in the node, and resort the nodes so that they are, again, in increasing order. And now here are the 2 least frequent letters. So we'll put those together. The C and the B together have frequency 25, and now the list is in this order. Then here are the 2 least frequently occurring, least frequently occurring letter and least frequently occurring subtree of letters. And so we put the D with the F and E tree like this. So 0 for the least frequent, the 14, and 1 for the second least frequent, the 16. So now I have a subtree like this. Pick the 2 least frequently occurring groups or letter, and 25 and 30 together make a 55, and now these 2 are all that are left, and I put those together into a search tree and get this structure, which is what we had before. And then this tree defines the dictionary, the assignment of code words to each letter. Very simple. What's the greedy part about it? At each stage, we simply grab the 2 least frequently occurring letters and say, well, let's put that in the tree, because as soon as you put something in the tree, it tends to get shoved farther and farther down as you go. And so this is a way of identifying things that should go as low in the tree as need be. Things that were selected last occur high in the tree, have the shortest code word lengths. And here's some pseudocode for that. First of all, we need a data type. So, well, it's like one of these. There's storage for a letter and a frequency, and then each of these will have 2 pointers to a type of itself, or a copy of itself, left pointer and a right pointer. Then you would initialize an array C. So there are n items, and each of those is of this type. So at that point, you would have created this structure where each of these guys starts out pointing to nil. It has no children. These are going to be leaf nodes. They will never have children. And then here's the algorithm to repeat n-1 times. So notice that we started out with 6 letters, and we had 5 stages of this. 1, 2, 3, 4, 5 stages of identifying the 2 least frequently occurring groups of letters. This routine calls a couple of others that are not written here, but let me just describe what they do. Remove lowest frequency. So from this array, search for the item with the lowest frequency, set a pointer to that node, and then remove that node from the array. And by the way, you would not, in actual practice, you would not store these characters in an array because you're doing a lot of inserting and deleting. You would probably use a linked list or a heap, as we'll talk about later in this class, and maybe you did in data structures as well. Anyway, representing as an array for simplicity. So basically popping the two least frequently occurring letters out of the array C and setting pointers to them, then creating a new node, call it R, set its left pointer and right pointer to P and Q, update its frequency as the sum of the two nodes that it's replacing. And when we create a node in this algorithm, it's not going to be a leaf, it's going to be one of these interior nodes, and so it has no content in itself. No letter is attached to these branch nodes. Then take node R, or the node that R points to, and insert it back into the array. So at each stage you delete two of them and you insert one of them. The number of nodes is going down by one each pass through this loop. At the end, do it one more time to get this final combination. Then you might as well clean up your array by deleting the last node and now return a pointer to the overall structure. So at the end, R points to the root node and it points to subchildren and to its children and so on down the tree. Regarding the efficiency of this algorithm, this loop obviously repeats n-1 times, and so these commands mask the complexity of what needs to happen here. It turns out that if you store the initial data structure in a tree itself, as we'll talk about later, that I can do insertion and deletion in log n times. So these are log n complexity operations. And therefore, since I'm doing n-1 of them, Huffman is of every case time complexity theta of n log n, which is a respectable complexity. So this is very doable. Note actually that I'm probably not terribly concerned about the complexity of this particular algorithm because this is just an algorithm to create the dictionary, the mapping of code words to bit strings. I only have to do that once, and then after that comes the usage of the code, the encoding and decoding. That's a heavy-duty operation, but it can be proven actually that the Huffman code as created by this algorithm is optimal in some sense, that it's a way of producing a variable length code that is as short as possible. Thanks.